You're listening to Worth Electronics What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists, and they're going to shine a light on some interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and today, radio modules. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. So today we are diving into the world of radio modules, and we're going to be exploring their very diverse applications across multiple industries. Now, whether it's remote control systems, wireless sensors, or even smart home devices, these modules play a pivotal role in bringing our innovation ideas to life. We'll be discussing short-range devices, also known as SRDs, as well as industrial, scientific, and medical, or ISM radio links. We're going to start by breaking down the fundamentals of radio technology and explain how we can enable seamless communication across multiple devices. We'll also give a clear understanding of SRD and ISM and their significance in the world of radio communications. Lastly, we'll touch on the communication between data rate and range in radio communications and examine their relationship and how they impact the performance of your wireless devices.
I'd like to quickly give you an overview of what is ISM or SRD. We'll have a look at some frequency bands, protocols, some RF basics, and thereafter some antenna types, a bit on the range and attenuation, as well as radio modules and some engineering tools. Yeah, let's start off. SRD, frequency bands. First of all, ISM stands for Industrial, Scientific and Medical, and SRD for Short Range Device. Now, those are the bands which are available for us, which we make use of, because they can be used without a government license, but nevertheless, they are subject to national radio regulations, depending on where you are, either Europe or the Americas, the East or Japan or Canada, wherever. They all have their different regulations, which still need to be taken care of. So these are bands, as it says, short-range devices, a few tens to hundreds of meters, not much more. And for that reason, we have a number of restrictions as well. Let's start off by the first slide here, the SRD frequency bands. Now, if you look here, we have about four popular bands that we use. The first one is the 169 megahertz band. Then there's the 433 megahertz band, the very popular 868 megahertz band, and also 2.4 gigahertz. These four bands are available to us. Now, in general, they are all limited in terms of power output. Basically, as you'll see here, the power output around about 14 dBm on average. There's one here which allows a bit more, 27 dBm or 500 milliwatt. But then also take care. We have something known as the duty cycle, which in all of these bands allows us a maximum time which we're allowed to go on to transmit, or TX. Now, this is not very much, but for most applications, more than sufficient, except if you intend to do radio or video transmission. Therefore, it's not intended. Basically, those are the four bands, and these are regulated by the European norm 300.220 for the sub 1 gigahertz and the 300.440 for above 1 gigahertz to 40 gigahertz. So these bands are regulated in Europe by the ETSI or FCC in America, IC in Canada. Let's have a look at the first idea or thought. The introduction, communication protocols. Obviously, all of the communication that goes via radio needs to be controlled and therefore is complex. And we have a intricate protocol to regulate and to control, to make sure that whatever goes over the radio here actually is received and makes sense on the receiving end. Now, invariably, the protocol defines the rules, the syntax, the semantics, and synchronization of the communication. And well, obviously it can be implemented either by hardware and or software. Now, in old days, if you had a plain set of a pair of cables, it was quite a bit easier. On the cable, you'd have a 0 or a 1 or an on and off. This is a bit more complex on the radio part, and obviously, apart from the radio module that does the job, we need an antenna, and the same on the opposite side for the receiving end. A bit of theory there. Let's have a look. What do we actually want to send via radio? Now, normally on a cable, I could just simply send hello world in a digital form, and the overhead, the control would be far less than with a radio signal. With a radio signal, we'd have something like a preamble, first of all, to get the signal going, to do some synchronization, a sync indicator, a header with certain information relating to the address, the destination, the sender. Then we actually have the payload in the actual package, and finally also a checksum, which verifies the integrity of our message. Now, as you can see, there is quite a bit involved to it. Yeah, I mentioned radio protocols. There are a number of protocols on the market. Probably very popular and well known is Bluetooth. Bluetooth Classic, the older, Bluetooth on 2.4 gigahertz. Bluetooth Low Energy, as from 4.2 onwards, we run 5.1 on our Bluetooth Low Energy modules. Then also Zigbee and Thread and so on. One of the bigger packages is our proprietary radio module, mostly on 868, but also on 169 and 433 megahertz. And 2.4 gigahertz. As you can see, the range is always a spin-off against data rate. If you want to send a higher data rate, you'd invariably have to forfeit some range and vice versa. So Wi-Fi in general has a fairly good range, very high data rate, whereas our proprietary radio modules probably have a bigger range. Now, obviously, LTE, 5G, and GSM, because of the repeater stations, have a very much bigger range. Bit of theory in the background. Now, let's get to the basics. How do we actually transmit our signal, our data? If you look at the left-hand top here, we have binary data of some other sort. We can't just put the bits into the air. We need to modulate them onto a carrier. Now, the carrier frequency invariably is either 868 megahertz or 2.4 gigahertz, a carrier frequency, and this gets modulated with the actual binary data. In this case, we have a simple system, which is 2 FSK. In other words, a frequency shift keying with two positions, one up and one down, and the RF signal would have two frequency components depending on the data, the zeros and ones. You'll see that on the left-hand side here in this lovely little picture here. The center being our carrier frequency, and if you look at the spectrum, up and down with a small offset would be the actual data, the zeros and ones. Now, all of this has to fit into a channel, so a limited bandwidth. You can see that on the right-hand top here, the oscilloscope picture, which I've taken and put in here. So this is our spectrum, our module spectrum. We need to stick within rules and limits in order to qualify and not to disturb other channels, other operators on the neighboring channels. And for that matter, we need to stay within emission limits. And you can see at the bottom here, for example, this would be an emission out of band. Right, that's a bit of theory. The center frequency and the bandwidth, which we need to stick in and adhere to. How do we actually get this information out into free space as a radio signal? And for that, invariably, we need an antenna. Now, the antenna is a conductor, copper or aluminium, or something suitable for conducting. fed through a coax cable or directly off the driver module. And invariably, we have a positive and a negative, or a ground. Now, what I have drawn or sketched here is a quarter wave antenna, therefore lambda over 4, and the equivalent as a negative, or it could be the ground as well. Now, this dimension is chosen because with this setup, we have a good, or we can provide a good standing wave ratio. Now, if we have a good standing wave ratio, SWR, we get the maximum energy transmitted into space as an electromagnetic wave. And for that, look at the blue line. The voltage should be a maximum at the points of the antenna and the current a maximum at the feeding side. And that is roughly the principle how it works. And if you optimize this, you get the best radio transmission. Now, the right-hand side, this lovely little red donut, is a symbolic representation of the direction of transmission of a dipole antenna. Obviously, in the Z direction, which would be the top and the bottom, we'd have the least signal strength and the maximum towards the side. Now, this is a pattern for a lovely omnidirectional dipole antenna. Many antennas are very much directional and therefore won't have such a lovely round donut shape, rather a distorted shape. Let's have a look at the left here. The negative part of the antenna could, on your PCB, also be part of the ground plane, and you would still have sufficient antenna on the positive side to actually get an electromagnetic signal out. Right, that was a bit of theory in the background. Let's have a look. What is the next one? Antenna types. Now, this is one of the problems or the questions we get asked very often. What is the best antenna to use? At the end of the day, it's up to you to decide which one is the most cost-effective, the best range. There are basically 3 or 4 types. The one is a basic chip antenna, which we use. You'll see at the bottom, which is just a few millimeter in size, maybe up to a centimeter. But inside there is a coil of wire wound in a cylindrical form. Then there's a PCB type of antenna, slightly bigger in size, but simply manufactured straight into the PCB in a zigzag fashion. The rear side of the PCB and the through holes would connect it. And if you stretch this into a straight wire, you'd actually, you should get something like 8.2, 8.3 centimeters for a quarter wave 868 megahertz antenna. Now you can do a bit of calculation yourself. The speed of an electromagnetic signal, I think, is 300,000 kilometers per hour. And if you calculate that, you should find a wavelength of 32 centimeters. A quarter wave is roughly 8 centimeters. Right, here we have a dipole antenna, which we use quite often. And I actually went along and cut one of these open, and I dismantled it to see what is inside this lovely little dipole antenna. And in fact, what we have in the top of it is a coiled antenna, or wound antenna. And the bottom part is the negative, a ground. Right, out of interest, then we have a folded dipole antenna. That is also an optional, and many other type of antennas with reflectors and attenuators and parabolic antennas, etc. So a big range of antennas. At the end of the day, it's a question of size and cost and range. A little bit more about theory. We start off with the signal strength with our transmitter. Now, we all know that we have limited power available, usually about 14 dBm, but also up to, we had it early on, what was it, 500 milliwatt. Now, these 14 dBm, in this case here, is what I have available with my transmitter. The first loss takes place in the transmitting antenna already. Then we have the free space in between. Now, this is a curved antenna because the loss into free space is in all directions, so it's a logarithmic formula. Then we have the losses in the receiving antenna, and what is left over is our signal margin, which we can actually use to actually receive the signal. Now, the free space is very little we can do about other than maybe taking care of line of sight and avoiding obstacles. What we can play around with as an engineer is both antennas, the transmitter and the receiver. And very, very critical is the height above ground. Now in free space we can very often use the freeze modular or freeze formula, which calculates as our estimated range. But in reality here on Earth, we rather tend to use the two-ray ground module. More about that a little bit later on. And for this reason here in the two-ray ground module, we have the height of the antenna on the transmitter and on the receiver, and we probably have some reflections which could attenuate or strengthen or weaken the signal on the receiving end. So very important, the height as well for the two-ray ground module. I'm going to leave that there. One more slide here. If we were to transmit straight into free space, this formula, this 4 pi r squared, comes into play, and that is part of the freeze formula as well, FRIIS. If you double the distance or the radius, the power left over is a quadratic function of the distance. I tried to here put together these two main formulas which we use very often to try and calculate a estimated range. Now the two-ray ground reflection module or formula is reliant on the height of the transmitter and height of the receiver. Don't go into detail of the actual formula. And the free space path loss, the freeze module, actually is reliant on this 4 pi, you see it again, and the R, which works very well in free space up to the moon or somewhere. But here on Earth, generally the first is a more relevant formula. I put these two together and played around a little bit here. The red and blue at the bottom are so-called free space formulas for 169 and 868 megahertz. And here you'll see that with a signal strength of 100 dBm, we could get quite high, up to 6, 8, or 10 kilometers. But that is not what really happens here on Earth. Therefore, we use the two-ray ground reflection module or formula at 1.5 meters antenna height, and then the picture looks quite a bit different. With around about, say, 100 dBm that we have available, we are just down to a few hundred meters at best. And that is what actually interests us here as engineers in the SRD range. Maybe one more slide here. The link budget is what we are ending up with after the power of the transmitter and the sensitivity of the sensed signal. The difference is what we have to work with. The link budget, we saw that in the earlier slide. Having a look at these two here, I took the first formula and entered some heights. The HT as 1 meter, HTNR 2 meters, and 6 meters for the gray. And here you can see that with a good antenna height, obviously we get a much better range. So the range increases with antenna height, and that is a crucial element of antenna theory. Right, here's a little trick question. The greatest man-made radio distance covered ever. 23 billion kilometers nowadays. Today, I checked that just recently. In fact, two years ago when I touched on this the first time, it was something like 21.5 billion. Wikipedia and Google makes it possible. Why do I actually mention this? Take a look at these figures and put them into the freeze formula and see it actually does work. What they have here in the Voyager satellite, in fact, 2 Voyager satellites, Voyager 1 and Voyager 2, they were both launched around about 1977, and they have sort of reached the outer edge of our solar system. So in fact, the signals and the pictures they still send back today take about 18 to 20 hours to arrive. But the quality of the pictures is so poor because we are far closer to our solar system ourselves now, so we can rather take the picture from here. Bit of interesting information. What do they use? They have 12.6 watt on a 3.6 meter parabolic antenna on the Voyagers. And they play around with an effective isotropic radiated power of about 89 decibel or dBm. They use a massive big 70-meter parabolic antenna stationed at the Goldstone Observatory in California, and they actually managed to receive down to 308.2 minus 308.2 decibel, which gives us a radio signal strength of 219 dBm. Now, this is way beyond what we can ever dream of as little engineers here in the world. We work in the SRD range and typically have about 14 dBm to our availability. Our antenna, for argument's sake, we lose about 5 dBi. We radiate roughly 9 decibel dBm. And if you look at a roughly 100 to 200 meter range, we have roughly 65 dBm loss, multiple path losses of another, say, 18 dBm. So I just estimated these values. I have a few walls in my path here, minus another 13. So very quickly, this adds up to minus 96 dBm loss over 100 meters, which allows me, or I end up with 87. Now, the receiving antenna, I haven't put that in, give it another minus 5 dBm, so I'm at 92. And our modules that we work with can receive anything, say, between 100 and 115, 120. So there is not much of a signal strength left over to work with. So those are the challenges for us as engineers here working on our little cheap radio modules, but they solve our problems. One more little hint I'd like to give, and that is on our homepage, we have a lovely little tool. Google for Red Expert, and in there you'll find a range estimator. Excellent little tool. What is in here are those two little formulas which we had previously. Enter the TX and RX height, the antenna above ground, the gains and losses, and the output power, and do a bit of calculation. In effect, this module here, the Tavos 3 with a PCB antenna, I just put in some figures, I get 37 meters on the two-way or two-ray ground module. And funnily enough, for the freeze model, I get 38, which isn't much more. But now I ask myself why. Probably because of the TX and RX height above ground, which I entered as 1 meter. Now, if I were to enlarge this to 2 or 3 meters, this difference should become significantly bigger. While I'm on this page, if you look on our homepage on the right-hand side, there's a link to all sorts of services, the technical support, which I'd like to point out. This here, just underneath it, a FAQ section, but also manuals and software downloads and various other niceties which you can have a look and play around with. I've summarized some cornerstones and some interesting facts. Have a look at these if you're interested. People always ask me, well, how many decibel is a watt, etc. So 0 dBm is 1 milliwatt, 10 is 10 milliwatts, 14, which is most of our modules, 25 milliwatt, and the one little module allows up to 27 dBm is 500 milliwatt. Now, as a rule of thumb, there's some lovely little rules here. Gain of 6 dBi is twice the distance, double the frequency is half the range or distance. And so on. 3 dB is roughly double the power, and 10 dBm, 10 times the power. Now you can do some calculations using these. It actually does work. Some factors which I'd like to point out, and keep this in mind when you do a design in, which we'll come to in the next slide, is the antenna. What type of antenna am I going to use? What is its gain? The sensitivity, body effects, and so on. Sensitivity I mentioned. The output power, we are very often just limited. Have a look at radio pollution, selectivity, and blocking. On the 2.4 gigahertz, obviously there's much more going on there. Be aware of that. And then the environment. Do we have a line of sight? That is very crucial. Obstructions in the line of sight, walls, tanks, trucks, reflections of buildings in the ground, multiple path fading. And then also lastly, the coding methods, whether it's Manchester FEC or DSSS, which is dynamic sequence spread spectrum, spreading the spectrum. So a lot of things we can play around with. Let's get to the one of the sort of nearing the end. Radio module design in. This is actually very simple and easy. How do you connect a radio mod to a host controller? Now, some radio modules actually have enough power and space and RAM to actually include some code on there. So you can just read some IOs and the module would do the necessary calculations and send out the radio package. But if that's not the case, like in the Tavos 3, we actually have a UART connection. We need to connect an antenna, either an external antenna to the left top pin here, which would be that pin. In fact, if you look at this here, you'll see that this, that was one too fast, that this is actually the connection for the PCB antenna. On the right-hand side, I highlighted the most important lines which you need. Obviously, is VCC and ground. You need the TX and RX, and obviously maybe the boot and the reset pin, and you could be up and running with your radio module. One last little point, the antenna path here on your PCB, try to give it a 50 ohm impedance. So do a bit of calculation. There's some examples in the internet as well, where you can do a bit of calculating on the path width and thickness in order to get a 50 ohm impedance, especially if your path to the antenna is fairly long. Right, the module does not work without any software, and we have a wireless connectivity software development kit, which has all sorts of C source code that you can play and use and integrate into your application. We also have USB sticks, which do the same as our evaluation boards. The USB stick has a FTDI driver on there. You plug that into your USB port, and with the necessary software, you can actually talk to the module and the stick does the rest for you. Right, what else do we have? Yeah, the SDK gives you all sorts of C code to integrate, compile into your application, and via UART or sometimes even SPI or I2C, you can talk to the module, and that's it. Yeah, there's one more little interesting thing I'd like to point out. GitHub, you can find all sorts of code there. Now, if you click on this little GitHub link here, you'll get to GitHub and find lots of suitable, useful information. Also on software downloads on our homepage, there are code snippets and examples for all sorts of modules and sensors, as you can see here. And I actually took a small part out of the, in the bottom for the Tavos 3, you see the order code, but there you can also download the wireless connectivity SDK. You can download the smart commander tool, very useful, and sometimes also the ACC tool. All available on our homepage. Right, this is something for all these software guys, all the programmers. Have a look. There's some very useful information and codes, examples and snippets for all sorts of modules which we have. The wireless connectivity SDK is available there. Proteus Connect Android is for the Bluetooth, the BLE. Featherwing, you might have a look at that. And then also obviously our sensors, all sorts of other applications. I'm coming towards the sort of second last slide here. We have a number of evaluation kits, which obviously have a big advantage that they make life easier for you. If you look at the right-hand side here, this module here is one of our older modules with a radio module on there. It has an FTDI driver on there and a USB connector. And you could actually solder in some headers here and do all sorts of tests and do power and current tests, etc., etc. Or plug in the antenna here if an external antenna is required. A picture here of our USB stick, in this case with an external antenna as indicated on the right-hand side here, but we also have them with internal PCB or chip antennas. The right-hand top here is one of our latest creations, the Setebos, or it could also be the Thione 1 or the Proteus 3. Have a look. This is a little development board. What you would need here is actually an FTDI cable and these header pins at the bottom here, and you could actually talk and manipulate this little evaluation board, which, the Setebos, more about that in the next slide. A little picture of our evaluation kit, which normally has everything inside that you need. Right, what does this give you? The antenna, the pin header, current measurements, SDK, FTDI, and so on. Let's have a look at the last slide. Folks, the clock is chasing me, but I'm on the end. Have a look, very interesting, the latest on our portfolio, the Setebos 1, which is a dual-purpose module based on the Nordic chip. It actually has, both stacks on it. The radio for the Bluetooth LE 5.1, Bluetooth Low Energy 5.1, as well as the 2.4 proprietary radio stack on it. Now, by using one of these chips or pins underneath the bottom of this board, connecting them high or low, you could actually, I don't see a red marker on here. Yeah, there we are. You can actually select the module to start either in a proprietary mode or in the BLE mode. And this is also available as a kit. Great fun. There's a bit of space on there to do some own programming. We have normally 6 or 5 I/O pins, which you can use for your own purpose of reading digital I/Os.
Now, it's important to remember that the world of radio communication is ever-changing, but you can keep up to date with our extensive line of radio modules, including Bluetooth and Wi-Fi, metering, GPS and GNSS, and cellular modules available at Worth Electronic online. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.